Okay guys, so in this video we are going to review the central limit theorem. So if you remember, where was the central limit theorem in our class? Well, remember the activity that we did when we were rolling the dice, trying to figure out the proportion of even numbers that we get from rolling a dice and what the distribution of all of our proportions were. So we got 10 dice, we rolled them, and maybe we got 7 out of the 10, right? So that's like 70%, and we plotted them all on the board, right? And then what we got was that the proportion, sample proportion, right, p hat, was normally distributed with a mean of p, right, and a standard error of square root of p 1 minus p over n. Now, this is usually called also the standard deviation, but in a sampling distribution, this is called a standard error, okay? Now, also keep in mind, our p and our p hat is always a number between 0 and 1 because it's the proportion of people that we have, or whatever the heck we're modeling. It can be people, it can be dice, it can be even numbers, whatever. So the proportion is always between 0 and 1. We can also put it as a percent. So when do we use the central limit theorem? So we use the central limit theorem, right, when we see keywords like sample proportion. So if that is in our problem, then this is when we're going to go ahead and use it. Some of the requirements, right, we need to make sure that it's a simple random sample, right? So it's an SRS. So everything has to be randomly selected. And the second one is that we need to have the expected number of successes have to be greater than or equal to 10. And the expected number of failures also have to be greater than or equal to 10. Now, in class, I put p hat. There should not be a p hat there. There should have been just a regular p. If we don't know what p is, then we use p hat. But usually this is what it is. And p is greater than or equal to 10. N times 1 minus p is greater than or equal to 10. Okay. So if you make sure that you also remember p, right? That's the population, right? Population proportion. So that's the big one that usually we don't know, but sometimes people say that we believe what it is. So that's what p is. P hat is our sample proportion. Okay, that's what we have. So if it satisfies these two, then it's good. Also, it has to be a big population. So the one that you really should be more focused on is trying to figure out, or try to, sorry, I was staring at the thing. I thought it wasn't recording. Just figure out that these conditions are sufficient, okay? All right, so let's go ahead and do a problem so that we can go ahead and remind ourselves on how we do this, right? So here's an example. And the example is the inventor of Morse code claimed that the most used English letter was E with a proportion of 0.12. So this means that the letter E appears in the one that we mostly use is E, and it appears 12% of the time. Okay, so find the probability that from 876 letters, so he gathered 876 letters, any random letters, the sample proportion will be greater than or equal to 13.5%. Okay, so the keyword here is sample proportion. That's what we want to highlight. That's sample proportion. So immediately when we see this keyword, just like we have here, that's when we're going to use this p hat. It's distributed, all this stuff, right? Now we need to make sure that it satisfies our requirements, right? So let's go ahead and put it down. NP has to be greater than or equal to 10, and n 1 minus p also has to be greater than or equal to 10. Okay, and not a hat. Okay, I put a hat last time and it shouldn't be there. Okay, now in this case, what is our p? Well, it depends. It can either be this 12%, this 0.12, or it can be this 13.5%. Now, which one is the one that we believe? Remember, p is the one that usually we believe, and we believe that is 0.12. So this is going to be our p. What is n? Well, n is the sample size, right? In this case, we got 876 letters, right? So this is going to be 876.12. Is this greater than or equal to 10? Well, let's find out. Well, I have my calculator right here, and we can see, all right, I'm going to put it right here. 876 times 0.12 gives me 105.12, which is definitely greater than 10, right? That's what we have. Now, let's go ahead and do it for this one. So even though it satisfied this one, and we need to make sure that the number of failures is also there. So the number of letters that are not E also has to be greater than or equal to 10. So 876, 1 minus 0.12, is that greater than or equal to 12? Okay, well, all we got to do is just plug this into our calculator, right? So I'm going to put 876, 1 minus 0.12, okay? And what we get is 770.88, which clearly is greater than 10. So our conditions are actually satisfied. So the requirements are good. So we're good with that, okay? So now that we know that this is satisfied, right? This is correct. Now we can go ahead and use this. So we have P hat is normally distributed with a mean of P and a standard error of P, 1 minus P divided by N. Okay, all we got to do now is just figure out what does this mean and what is this. Okay, so let's go ahead and plot them. So P hat is this normally distributed. Well, P in this case is just 0.12. Then comma, square root 0.12, 1 minus 0.12 divided by 876. Okay. Okay, so this stays the same. And let's just figure out what this is. Okay, so we're going to go back to our calculator, right? And this can be a little bit hard because putting it in the calculator is where I've seen that most students make a mistake. So just be very careful of that. So what we're going to get, so I'm going to put second square root 0.12, 1 minus 0.12 divided by, oh, damn it. Okay, second square root. Let me do this. Let me put this. Because this actually helps. If you have the TI-36, this is going to help. So 0.12, 1 minus 0.12 divided by the total 876, right? What is that going to give me? I got that number. So let's round to the nearest, to 3 decimal places. So this is going to be 0.011. Okay, so let's just round it to there. Okay, so now we know what the mean is and we know what the standard error is, okay? So all we got to do now is, well, let's go back to the problem. Okay, so now that I know the mean and now that I know the standard error, let's try to figure out what exactly are we asking for? We are asking for the probability that the sample proportion will be greater than or equal to 13.5%. So let's draw a picture, okay? Always try to draw a picture. What was the mean? The mean is 0.12, okay? 0.12. What is the value that we're looking for? This value, right? Well, this value is also, as a decimal, is 0.135, right? Which is a little bit more than this, right? So this is 0.135. Where am I shading it? Everything that's greater than or equal to. So everything greater than all of this, right? So we're looking for this area. This is the area that we want, right? So this is our normal distribution. I have a mean, I have a standard error. Then I can go ahead and use inverse normal or normal CDF. Well, in this case, we know the X value, so we're using normal CDF. So normal CDF, okay. And then I'm gonna go ahead and put, what is my lower bound? My lower bound is from 0.135. What is my upper bound? Well, this goes all the way really, really large, right? So I'm just gonna put like 10000, whatever. It doesn't really matter if this is big. I mean, the standard error is really, really small too, but anyways. Mean 1.12, standard error 0.011. Okay, so let's put that into my calculator. In our calculator, so remember how we activate it. So second data, gonna go to distributions, right? Go all the way down to normal CDF right here. Our mean is 0.12, 0.12. Our standard error is gonna be 0.011. Enter. Our lower bound is going to be 0.135. As you can see, this is my lower bound, 0.135. And then our upper bound is we're just going to leave it as this. So calculate, and what do we get? We get approximately 0.086. Okay, that's my answer. I know it's a little blurry. Sorry, you guys. That is my answer. Okay. Okay, so, this kind of makes sense, right? Because the standard deviation is really, really small, right? It's not a lot, right? But yep, this is what we got. Okay, so just a couple things. Make sure that you are able to satisfy the requirements, right? So step 1, make sure that they satisfy, because if they don't satisfy, then we can't do anything. Once they are satisfied, then we go to step number 2, which is plugging in all the values, right? once we have all the values, step number 3, draw a picture to see where my lower bound and my upper bound are going to be. And then step number 4, just go ahead and use normal CDF to calculate the probability. Okay, so hopefully there is no mistake around here, right? And yeah, so this was the end of central limit theorem. Okay.